What if I told you that the speed of light isn't actually a speed at all? That we've been thinking about it wrong this entire time? And that the moment we measured it, we accidentally discovered something so disturbing about the nature of reality that physicists are still arguing about it today. You see light every single day. Right now, photons are bouncing off the screen, traveling through space, hitting your retina, and you think you understand it. But here's the thing that's going to haunt you for the rest of this video. Light doesn't experience time. From a photon's perspective, it's created and destroyed in the same instant, even if it travels for billions of years from our perspective. And the craziest part? We only know this because of a failed experiment involving a spinning wheel and a mountain. An experiment that was supposed to prove something completely different. An experiment that accidentally broke physics. The speed of light is 299,792,458 meters per second. But that number? It wasn't discovered. It was decided. And when you understand why, your brain is going to short circuit. Before we dive into this reality-warping journey, do me a favor. Smash that like button and subscribe, because I guarantee you've never heard this story told this way before. And drop a comment telling me what country you're watching from and what time it is right now, because that simple fact is about to become deeply weird by the end of this video. Let's start with what seems like a simple question. How fast does light travel? You might think this is obvious now, right? We have the number. But think about this for a second. Really think about it. How would you even begin to measure something that moves faster than anything else in the universe? You can't use a stopwatch. You can't use a radar gun, because radar guns use light. It's like trying to measure how fast your car is going by looking at your speedometer while you're sitting still. For most of human history, people didn't think light traveled at all. Aristotle, one of the greatest minds in ancient Greece, believed light was instantaneous. It just appeared. You open your eyes and boom, you see, no travel time. And honestly, can you blame him? Have you ever noticed light taking time to get somewhere? When you flip a light switch, the room illuminates instantly, right? But here's where it gets interesting. Around 1676, a Danish astronomer named Ole Ratmer was doing something completely unrelated to measuring light speed. He was trying to create better maritime maps by tracking the eclipses of Jupiter's moon, Io, and he noticed something bizarre. The eclipses weren't happening when they were supposed to. Think of it like this. Imagine you have a friend who's always exactly on time. Every day at 3 p.m., they text you. Then suddenly, their texts start arriving at 3:02 p.m., then 3:05 p.m., then back to 3 p.m. You'd think something was wrong with them, right? But what if the problem wasn't your friend at all? What if time itself was changing? That's what Ratmer realized. The eclipses weren't early or late. Light was taking different amounts of time to reach Earth, depending on where Earth was in its orbit. When Earth was farther from Jupiter, the light took longer to get here. When Earth was closer, it arrived faster. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. That put the speed of light at about 220,000 kilometers per second. Not perfect, but incredibly close for 1676. And here's what's mind-blowing. Ratmer figured this out without ever directly measuring light. He measured the universe and let it tell him how fast light moved. But most scientists didn't believe him. They thought his timing was just off. Because accepting that light had a speed meant accepting something deeply uncomfortable. When you look at the stars, you're not seeing the present. You're seeing the past. Every star is a time machine, and the universe is showing you a movie that's already over. Now here's where things get wild. Fast forward to 1849, France. A physicist named Hippolyte Fizeau decides he's going to measure the speed of light directly, not using astronomical observations, but right here on Earth. His idea? Brilliantly simple, but here's what will blow your mind. He essentially tried to race light, and he won. Sort of. Picture this. Fizeau sets up a spinning-toothed wheel. Imagine a gear with 720 teeth. He shines a beam of light through a gap between the teeth, bounces it off a mirror 8 kilometers away, and the light comes back. Now, if the wheel isn't spinning, the light passes through the same gap it left through. Easy. But here's where it gets clever. Fizeau starts spinning the wheel faster and faster. At certain speeds, the wheel rotates just enough while the light is traveling that the light comes back and hits a tooth instead of a gap. The light gets blocked. Then, spin it even faster, and the light passes through the next gap. It reappears. Think of it like trying to throw a ball through a closing door. If you time it perfectly, it gets through. Too slow, the door closes. But if the door is moving fast enough, it might open again just in time. Fizeau could calculate the speed of light based on how fast the wheel was spinning when the light disappeared and reappeared. His result? 315,000 kilometers per second. Only about 5% off from the actual value. But here's the twist that nobody talks about. Fizeau didn't just measure the speed of light. He proved something philosophers had been arguing about for centuries. Light is not instantaneous. It travels. It takes time. Which means, when you look at yourself in a mirror, you're not seeing present you. You're seeing past you. Only by a few billionths of a second, sure, but still the past. Every single thing you've ever seen in your entire life is history. You have never, not once, experienced the present moment. You're always living in the past. Let that sink in. All right, so by the late 1800s, scientists had a pretty good idea of how fast light traveled. Problem solved, right? Wrong, because now they had a much bigger question. What is light traveling through? Think about it. Sound travels through air. Ocean waves travel through water. If you remove the air, sound can't travel. That's why there's no sound in space. So what medium does light travel through? Space is empty, right? How can light travel through nothing? Scientists proposed something called the luminiferous ether, an invisible, weightless substance that filled all of space and allowed light to propagate like ripples through water. Seems reasonable. Except, how do you prove something invisible and weightless exists? Enter Albert Michelson and Edward Morley in 1887. These two scientists designed what should have been a triumphant confirmation of the ether's existence. Instead, they accidentally destroyed the entire foundation of physics. Here's their logic. If the ether exists and Earth is moving through it, then light should move at different speeds depending on whether it's moving with Earth's motion or against it. Just like if you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing still outside sees the ball moving at 120 kilometers per hour. They built an incredibly sensitive device called an interferometer. It splits a light beam in two directions, one parallel to Earth's motion through the ether, one perpendicular. If light travels through ether, these two beams should take different amounts of time to complete their journey because one is moving with the ether and one is moving across it. Are you ready for what they found? Nothing. Absolutely nothing. No difference. No matter which direction they pointed their device. No matter what time of year. The speed of light was exactly the same in every direction. This wasn't just surprising. This was reality-breaking. It's like getting on a train, throwing a ball, and having someone outside the train measure the ball moving at exactly the same speed as if the train wasn't moving at all. It violates common sense. Scientists were so disturbed by this result that they spent years trying to explain it away. Maybe the ether was being dragged along with Earth? Maybe the apparatus was flawed? Maybe they measured wrong? But here's what will haunt you. They didn't measure wrong. Reality is just stranger than we thought. The speed of light doesn't add or subtract based on the motion of the source or observer. It's always the same. Always, which means everything you think you know about how motion works is wrong. Speed, distance, time, none of these things mean what you think they mean. And it took the most famous scientist in history to figure out why. In 1905, a 26-year-old patent clerk named Albert Einstein was sitting in his office in Bern, Switzerland, and he did something audacious. He looked at the Michelson-Morley result and said, "What if the experiment isn't wrong? What if our understanding of space and time is wrong?" And with that single thought, he shattered 3,000 years of physics. Einstein's insight was this: what if the speed of light is always the same, not because there's some weird coincidence, but because that's a fundamental law of the universe? What if the speed of light is the one constant, and everything else, space, time, distance, has to bend and flex to keep light speed constant? Think of it like this. Imagine you're driving a car, and no matter how hard you press the gas pedal, your speedometer always reads exactly 100 kilometers per hour. Always. When you think you're speeding up, the car actually gets heavier. When you think you're slowing down, distances get shorter. The speedometer never changes. That's our universe. The speedometer for light never changes. Instead, space shrinks. Time slows down. Mass increases. Reality warps itself to keep the speed of light constant. This is special relativity. And here's where it gets truly disturbing. This means that when you're moving at high speeds, you're literally experiencing time differently than someone standing still. Time isn't universal. There's no cosmic clock that everyone agrees on. Your now and my now are different if we're moving relative to each other. But Einstein went even further. He realized that if the speed of light is constant and nothing can go faster than light, then the speed of light isn't just a speed. It's the speed of causality itself. It's the maximum speed that cause and effect can propagate through the universe. It's the speed limit of reality. And here's the number that proves it. E equals mc. You've seen this equation. But do you understand what it means? That little c in there? That's the speed of light. And Einstein is saying that energy and mass are the same thing, connected by the speed of light squared. Light speed squared is roughly 90 quadrillion meters per second squared. That's why a tiny amount of mass, like the mass in an atomic bomb, contains a terrifying amount of energy. That's why the sun can burn for billions of years. That's why you exist. The speed of light isn't just some random number. It's woven into the fabric of reality itself. And measuring it wasn't just about finding a speed. It was about discovering the fundamental structure of space and time. After Einstein, you might think the story ends. We understand light speed. We understand relativity. Done, right? Not even close. Because by the mid-20th century, scientists realized something crucial. If the speed of light is this fundamental constant that doesn't change, we can use it as a universal standard. We can base all of our measurements on it. In the 1960s and 70s, with the invention of lasers, scientists could measure the speed of light with unprecedented accuracy. Lasers are special because they produce light that's coherent. All the light waves are perfectly in sync, marching in lockstep. This makes them perfect for precision measurements. Here's where it gets interesting. In 1972, scientists at the National Institute of Standards and Technology measured the speed of light to be 299,792,456.2 meters per second, with an uncertainty of only about 1 meter per second. That's insanely precise. That's like measuring the distance from New York to Los Angeles and being accurate to within the length of a single footstep. But then scientists realized they had a problem. A beautiful problem. The speed of light was now more precisely known than the meter itself. The meter was defined as a physical object, a platinum iridium bar kept in a vault in Paris. But that bar could change length with temperature. It could be damaged. It wasn't stable enough for our measurements of light. So in 1983, scientists did something radical, something that still confuses people today. They stopped measuring the speed of light. Instead, they defined it. They said, the speed of light is now exactly 299,792,458 meters per second. Not approximately, exactly, by definition. Wait, what? How can you just decide what the speed of light is? Here's the mind-bending part. They redefined what a meter is. A meter is now defined as the distance light travels in exactly 1,299,792,458 of a second. We flipped the equation. Instead of measuring light speed using meters, we now define meters using light speed. Think about what this means. The meter, this unit you use every day, isn't based on a physical object anymore. It's based on time and the speed of light. And time? Time is defined by atomic clocks, which count the oscillations of cesium atoms. So your height, the size of your house, the distance to work, all of it is ultimately defined by the vibrations of atoms and the speed of light. Reality is measuring itself with itself. Okay, here's the question that's been bothering you. Why? Why is the speed of light the speed limit? What happens if you try to go faster? Here's what will blow your mind. You can't. And it's not because we haven't built a fast enough spaceship. It's because the universe literally won't allow it. Remember Einstein's equation, E equals mc? Let's dig deeper into what happens when you try to accelerate something to light speed. Imagine you're in a spaceship and you're accelerating. You fire your rockets, you go faster. Fire them again, faster still. But here's the weird part. As you approach the speed of light, something bizarre happens. Your mass increases. Not because you're gaining material, but because of relativity. The energy you're putting into acceleration is being converted into mass. And the faster you go, the more massive you become. And the more massive you are, the more energy it takes to accelerate further. As you approach light speed, your mass approaches infinity. And to accelerate something with infinite mass, that takes infinite energy, which doesn't exist. Think of it like this. Imagine you're pushing a car, and every meter you push it, the car gets heavier. First it's a sedan, then it's a truck, then it's a bus, then it's a building. Eventually, you're trying to push the entire mass of the planet Earth. You can push as hard as you want. You're not moving that car another inch. That's what happens as you approach light speed. The universe itself pushes back harder and harder until it becomes literally impossible to go any faster. But here's the truly weird part. From your perspective in the spaceship, you're not getting more massive. You feel perfectly normal. It's the universe outside that's getting weird. Distances contract. The stars compress into a tunnel of light ahead of you. Time outside your ship speeds up. You could travel thousands of light years and only age a few years yourself. This is called time dilation, and it's not theoretical. It's been proven over and over again. We've put atomic clocks on airplanes, flown them around the world, and when they land, they're behind clocks that stayed on the ground. Only by nanoseconds, but measurably behind. GPS satellites have to account for relativistic time dilation, or they'd accumulate errors of several kilometers per day. The fact that your GPS works is proof that Einstein was right. And here's something that will keep you up at night. From a photon's perspective, a particle of light, no time passes at all. Ever. A photon could travel from the edge of the universe through billions of light years, and from its perspective, the journey takes zero time. It's born and dies in the same instant. Light doesn't experience time, which means in a very real sense, light doesn't experience existence. It's everywhere it will ever be, all at once. Now we need to talk about something that's going to make your brain hurt. Because when physicists started measuring light at quantum scales, the scale of individual photons, they discovered something so disturbing that it's still debated today. Here's the setup. You take a beam of light and you send it through two narrow slits. On a screen behind the slits, you'd expect to see two bright lines where the light passes through, right? Wrong. You see an interference pattern. Stripes of light and dark. This happens because light acts like a wave, and waves from both slits overlap and interfere with each other, sometimes adding together, bright, sometimes canceling out, dark. Okay, that's weird but acceptable. Light is a wave. Waves interfere. Fine. But then, scientists got better equipment. They could send one photon at a time through the slits. One single particle of light. It has to go through one slit or the other, right? Can't split itself. But when you do this experiment, sending one photon at a time, over and over, the pattern that builds up is still the interference pattern. Individual photons, somehow, are interfering with themselves. A single photon acts like it goes through both slits at once. Now here's where it gets absolutely insane. Scientists decided to watch which slit the photon goes through. They put a detector at each slit to see which path the photon takes. And the moment they did this, the interference pattern disappeared. The photons started behaving like particles, going through one slit or the other. The act of measuring which path the photon took changed how the photon behaved. This is the famous observer effect in quantum mechanics. And here's what's deeply disturbing. It's not about consciousness or some mystical power of observation. It's about measurement itself. The photon exists in a state of superposition, going through both slits simultaneously, until something interacts with it to measure it. Then, and only then, does it choose a path? But here's the question that haunts physicists. What counts as a measurement? Does the detector count? Does a human looking at the detector count? Does the universe just know when something is being measured? Some physicists believe that the photon creates two parallel universes. One where it goes through the left slit, one where it goes through the right slit. In each universe, a different version of you sees a different result. This is the many worlds interpretation. Other physicists believe the photon's wave function collapses when measured, going from a state of probability to a state of actuality. But what causes the collapse? Nobody knows. And here's what should terrify you. Every single thing you've ever seen has gone through this process. Every photon that's ever hit your retina was in a state of quantum superposition until it interacted with your eye. Which means that in a very real sense, observation creates reality. You're not just watching the universe. You're collapsing quantum wave functions billions of times per second just by existing. The speed of light isn't just a speed. It's the speed at which information, at which reality itself, propagates through the universe. Take a moment right now. Look around you. Look at the walls, the ceiling, your hands. Everything you're seeing is light that's bounced off those objects and traveled to your eyes. But here's what you need to understand. That light took time to get here. Not much time, maybe a few nanoseconds, but time nonetheless, which means you're not seeing the present. You're seeing the past. Always. Constantly. Forever. When you look at the sun, you're seeing it as it was 8 minutes ago. The sun could have exploded 7 minutes ago, and you wouldn't know it yet. You'd be sitting there, enjoying the sunshine, completely unaware that the sun no longer exists. For one more minute, you'd live in a universe with a sun, while someone living in the actual present would live in a universe without one. When you look at the stars, you're seeing them as they were years, decades, centuries, even millions of years ago. Some of those stars are already dead. You're seeing ghost light from stars that no longer exist. The universe is showing you a history book, and you think it's live television. But it gets more personal than that. When you look at another person, the light takes time to travel from them to you. Only a few nanoseconds, but time nonetheless. Which means when you look into someone's eyes, you're seeing them as they were in the past. You and that person are existing in slightly different time frames. You're never truly synchronized with anyone. And here's something even weirder. Because of relativity, two events that are simultaneous for you might not be simultaneous for someone moving at a different speed. Your now is different from someone else's now. There is no universal present moment. The concept of now is relative. This has profound implications. It means that in a very real sense, the past, present, and future all exist simultaneously. They're just different slices through the four-dimensional structure of spacetime. Your past self still exists in the past. Your future self already exists in the future. Time isn't a river flowing from past to future. It's a landscape that already exists in its entirety, and you're just moving through it. Think about what this means for free will. If the future already exists, are your choices predetermined? Or is the universe branching into multiple futures based on quantum probabilities? These aren't just philosophical questions. They're questions about the fundamental nature of reality that emerge directly from measuring the speed of light. And here's something that should fill you with awe. You are made of atoms that were forged in the hearts of stars. Those atoms traveled through space, were assembled into molecules, and eventually became you. And the force that guided that entire process, the force that allowed stars to shine and energy to flow and chemistry to happen, is fundamentally limited by the speed of light. You exist because of light. You see because of light. And the speed at which light travels determines the structure of space, the flow of time, and the very possibility of causality itself. Every moment you experience, every thought you have, every action you take, all of it happens within the constraints set by the speed of light. You're living inside a universe with a speed limit, and that speed limit is why atoms can exist, why chemistry works, why stars shine, why you can exist at all. So where are we now? What are scientists doing with our understanding of light speed in the 21st century? Here's what will blow your mind. We're using the constancy of light speed to hunt for gravitational waves, ripples in spacetime itself. In 2015, the LIGO experiment detected gravitational waves for the first time, confirming another prediction Einstein made 100 years earlier. How does LIGO work? It's essentially a giant Michelson-Morley interferometer, but instead of looking for the ether, it's looking for tiny distortions in space itself. When a gravitational wave passes through Earth, it literally stretches and compresses space. LIGO can detect changes in distance smaller than the width of a proton. The experiment splits a laser beam, sends it down two 4-kilometer-long arms at right angles, bounces it off mirrors, and brings it back together. If space is distorted by a gravitational wave, one arm becomes slightly longer than the other, and the laser beams become slightly out of sync. By measuring this tiny difference, using the constancy of light speed, we can detect gravitational waves from black holes, colliding billions of light years away. Think about that. We're using the speed of light, which we measured with spinning wheels and lasers, to detect waves in the fabric of spacetime itself. We've gone from, how fast does light go? To, how does the universe ripple when massive objects collide? But here's where it gets even more mind-bending. Some physicists are now asking, what if the speed of light hasn't always been constant? What if in the early universe, right after the Big Bang, light traveled faster than it does now? This is called variable speed of light cosmology, and it could solve some major mysteries about the early universe. The universe appears to be uniform in temperature in all directions, but according to standard cosmology, different parts of the universe shouldn't have had time to interact and equalize temperature, unless light was faster back then. This is still highly speculative. Most physicists think the speed of light is truly constant. But the fact that we're even asking these questions shows how fundamental the speed of light is to our understanding of everything. And then there's quantum entanglement. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and hated it because it seemed to allow information to travel faster than light. But here's the twist. Quantum entanglement doesn't actually allow faster than light communication. You can't send a message through entanglement. The correlations are real, but they can't be used to transmit information. The universe has a built-in protection against causality violation. Light speed remains the limit, unless we figure out how to manipulate spacetime itself, which brings us to the wildest frontiers of modern physics: warp drives and wormholes. Here's a question that's haunted science fiction for decades. Can we go faster than light? The answer, according to Einstein, is no. Nothing can move through space faster than light. But here's the loophole that makes physicists' eyes light up. What if we don't move through space? What if we move space itself? In 1994, a physicist named Miguel Alcubierre published a paper describing a theoretical warp drive. The idea is this: you create a bubble around your spaceship. In front of the bubble, you compress space. Behind the bubble, you expand space. The spaceship itself doesn't move through space. Space moves around the ship. Inside the bubble, you're standing still, so you're not violating light speed. But the bubble itself can move faster than light because there's no limit to how fast space can expand or contract. In fact, space is expanding faster than light right now in distant parts of the universe. We can't see those regions because their light will never reach us. So theoretically, you could travel to a distant star in days or weeks, while only experiencing a few hours inside the ship. You'd have circumvented the light speed limit, not by going faster, but by redefining what distance means. Sounds perfect, right? Here's the problem. Creating an Alcubierre bubble requires exotic matter with negative energy. As far as we know, such matter doesn't exist in large quantities. You'd need more negative energy than exists in the observable universe. Small detail. But some physicists think there might be ways around this. Maybe we can use the Casimir effect, a quantum phenomenon that creates negative energy in small spaces. Maybe we can manipulate dark energy, which appears to have negative pressure. These are all highly speculative, but they're not impossible. And then there are wormholes, shortcuts through spacetime. If you could create a stable wormhole, you could step through and emerge light years away instantly. Again, you're not traveling faster than light through space. You're taking a shortcut through a higher dimension. The problem? Wormholes, like warp drives, require exotic matter to stay open. Try to send anything through a wormhole without exotic matter, and the wormhole collapses faster than light can traverse it. The universe really doesn't want you breaking causality. But here's what's fascinating. None of these concepts violate relativity. They're all solutions to Einstein's equations. They're allowed by the math. They're just probably impossible to implement with the physics we know. Which brings us to a disturbing question. What if advanced civilizations have figured this out? What if there are aliens out there who've learned to manipulate spacetime, who travel through warp bubbles or wormholes? Would we even be able to detect them? Maybe the reason we haven't found alien civilizations isn't because they don't exist. Maybe it's because they're all using faster than light travel, and we're stuck looking for radio signals that take centuries to travel between stars. We're using horse and buggy technology to search for civilizations that might have starships. Let's talk about something that connects the speed of light to one of the biggest unsolved mysteries in physics: black holes. Here's what happens when light encounters a black hole. At a certain distance from the black hole, called the event horizon, the escape velocity equals the speed of light. Inside the event horizon, not even light can escape. Space is falling into the black hole faster than light can climb out. Think about what this means. A black hole isn't just a really strong gravitational well. It's a region of space where the very geometry of spacetime has been so extremely warped that the future direction, the direction time flows, points inward. Once you cross the event horizon, Your future is inside the black hole. There's no going back, because going back would mean going backward in time. Light speed sets the boundary between can escape and can't escape. The event horizon is literally defined by the speed of light. But here's where it gets really disturbing. Stephen Hawking discovered that black holes aren't actually perfectly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over incredibly long timescales, black holes evaporate, and this creates a massive problem called the information paradox. When things fall into a black hole, they carry information, the exact arrangement of particles, the quantum states, everything that makes them what they are. When the black hole evaporates, where does that information go? If it's destroyed, that violates a fundamental principle of quantum mechanics. Information can't be destroyed. But if it's preserved in the Hawking radiation, how? The radiation seems to be perfectly thermal, containing no information about what fell in. Some physicists think the information is encoded on the event horizon itself, in a 2D hologram. Others think it's released in subtle correlations in the Hawking radiation. Still others think information is destroyed, and quantum mechanics needs to be modified. This isn't just an abstract puzzle. It's a fundamental question about the nature of reality. And it all comes down to the speed of light defining where the event horizon is. Here's something even weirder. From the perspective of someone falling into a black hole, nothing special happens at the event horizon. You cross it and keep falling. But from the perspective of someone watching from outside, you never quite reach the event horizon. Time dilation becomes infinite. They see you slowing down, getting redder and dimmer, frozen forever at the edge. Two observers, two completely different realities. And both are right. This is what relativity does. It makes reality observer-dependent. The speed of light is the conversion factor between these different perspectives. Let's zoom out, way out, to the scale of the entire observable universe. The observable universe has a radius of about 46 billion light years. Wait, didn't I say the universe is only about 13.8 billion years old? How can we see things 46 billion light years away if light has only had 13.8 billion years to travel? Here's the answer. Space itself is expanding. The galaxies we see 46 billion light years away emitted their light when they were much closer to us. But while that light was traveling, space expanded, stretching the light waves and moving those galaxies farther away. The speed of light limits how fast information can travel through space, but there's no limit on how fast space itself can expand. In fact, the most distant visible galaxies are moving away from us faster than light because space is expanding so rapidly. This means there's a cosmic horizon, a boundary beyond which we can never see, no matter how long we wait. Galaxies beyond this horizon are receding faster than light, and their light will never reach us. Ever. We are cosmically isolated from huge portions of the universe. And here's something that will haunt you. Because of accelerating expansion driven by dark energy, this horizon is actually shrinking. Galaxies we can see now will eventually cross this horizon and fade from view. In trillions of years, future civilizations will look up at the sky and see almost nothing, just their local group of galaxies in an otherwise empty universe. They'll have no evidence of the Big Bang, no evidence of cosmic expansion, no evidence of the vast universe we can see today. They'll think they live in a small, static universe. Everything we know about cosmology will be unlearnable for them. This raises a disturbing question. What are we missing? What evidence has already faded beyond our cosmic horizon? What parts of the universe's history or structure are no longer visible to us because the light has been stretched beyond detection? The speed of light doesn't just limit how fast we can travel. It limits what we can know. There are regions of the universe that are forever unknowable, forever unobservable, simply because the light from them hasn't had time to reach us, or never will. And yet, Despite this cosmic isolation, light connects us to the most distant parts of the universe we can see. When you look at the cosmic microwave background, the afterglow of the Big Bang, you're seeing light that has been traveling for 13.8 billion years. You're seeing the baby picture of the universe, carried to you by photons that have been journeying through space for longer than Earth has existed. Every photon that hits your eye is a messenger from the past, carrying information across vast gulfs of space and time. And the speed at which those photons travel determines everything about how we perceive and understand the cosmos. Here's something that's going to tie everything together in a deeply unsettling way. Remember how I told you that in 1983, we stopped measuring the speed of light and just defined it instead? Let's think about what this really means. The speed of light is now exactly 299,792,458 meters per second because we say it is. Not because we measured it to be that, but because we defined the meter based on that number. But here's the conspiracy level question. How do we know that the speed of light is actually constant? We've based our entire system of measurement on the assumption that it doesn't change. But what if it does change and we can't detect it because our rulers are changing too? Think about it like this. Imagine you're measuring your height with a rubber ruler, but you don't know it's rubber. Every time you grow an inch, the ruler stretches by exactly the same amount. You'd measure yourself and get the same height every time. You'd think you weren't growing, but actually both you and the ruler are changing together. That's potentially what's happening with the speed of light. If light speed changed, distances would change in lockstep because distances are defined by light speed. We'd have no way to detect the change. Some physicists have seriously proposed that the speed of light might have been different in the early universe. Others have suggested it might vary slightly depending on the energy of the photons. These are fringe ideas, but they're not completely crazy. Here's what's really mind-bending. We can't directly measure the one-way speed of light. Every measurement we've ever made actually measures the round-trip speed, light going from point A to point B and back to point A. Why does this matter? Because to measure the one-way speed, you'd need synchronized clocks at points A and B. But how do you synchronize clocks that are far apart? You send a light signal. But that assumes you know the one-way speed of light, which is what you're trying to measure. It's circular. Physicist Albert Einstein actually acknowledged this. He said we have to assume the one-way speed of light equals the round-trip speed divided by 2. We assume light takes the same time to go from A to B as it does to return from B to A. But what if it doesn't? What if light travels instantaneously in one direction and half speed in the opposite direction? The round trip would average out to the same speed we measure, but the one-way speeds would be radically different. And here's the kicker. This wouldn't violate relativity. Relativity only requires that the round-trip speed is constant and the same for all observers. This sounds insane, but multiple physicists have published papers showing this is logically consistent. We could live in a universe where light goes infinitely fast toward the north and at half speed toward the south, and we'd have no way to prove otherwise. Our measurements would look identical. Now, most physicists think this is just a philosophical curiosity. The simplest assumption is that light speed is the same in all directions. But the fact that we can't prove it, that we've based our entire understanding of physics on an untestable assumption, should make you uncomfortable. Here's another disturbing thought. Every fundamental constant in physics might be changing slowly over cosmic time, and we wouldn't necessarily notice if they all changed together in the right proportions. The fine structure constant, the gravitational constant, the speed of light. What if they're all slowly drifting? Some astronomers have looked at light from distant quasars and claimed to see tiny variations in the fine structure constant. If true, it would mean the laws of physics are slightly different in different parts of the universe or at different times. Other astronomers dispute these findings, but the possibility remains. We think we've measured the speed of light, but really, we've woven it so deeply into our system of measurement that we can't separate our measurements from the thing being measured. We've created a self-referential system where light speed defines distance, distance defines light speed, and we're trapped inside, unable to step outside and see if the whole system is drifting. Now we're going to go somewhere really weird. And I need you to stay with me, because this connects everything we've talked about to something deeply personal: your consciousness. Here's a fact that neuroscientists know. Nerve signals in your body travel at speeds between 0.5 to 120 meters per second, depending on the type of nerve. That's incredibly slow compared to light speed. Light travels at 299,792,458 meters per second. Nerve signals travel at least 2.5 million times slower. This means there's a significant delay between when something happens to your body and when your brain registers it. When you stub your toe, it takes about 0.02 seconds for the pain signal to reach your brain. Your brain then takes additional time to process that signal and create the conscious experience of pain. But here's what's weird. You don't experience this delay. Your consciousness feels immediate and unified. You feel like you exist as a single, coherent entity experiencing everything in the present moment. But you're not. You're a distributed system with significant communication delays, and your brain is constantly lying to you to create the illusion of a unified, instantaneous experience. Your brain backdates events. It receives delayed signals from your body and timestamps them as if they happened earlier, creating the illusion that your consciousness is synchronized with reality. But it's not. You're always living in the past, assembled from delayed signals, and your brain is telling you it's the present. Now here's where it connects to light speed. The speed of light sets the absolute minimum delay for any information transfer. Even if we could build computers using light instead of electricity, even if we could enhance our nervous systems with light speed communication, we'd still be limited by the speed of light. Imagine a future where humans have expanded throughout the solar system. You're on Mars, having a conversation with someone on Earth. Mars is, on average, about 12.5 light minutes away from Earth. That means anything you say takes 12.5 minutes to reach. Earth and their response takes another 12.5 minutes to get back to you. A 25-minute delay for every exchange. You can't have a real-time conversation. You can't have a shared experience. You're forever isolated by the speed of light delay. And this isn't a technology problem. This is a fundamental constraint of the universe. Now scale that up. Imagine humanity spreads to other star systems. Alpha Centauri is 4.37 light years away. Send a message. Wait 4.37 years for it to arrive. Wait another 4.37 years for a response. Almost 9 years for a single back and forth. No shared news, no collaborative projects, no unified culture. Just isolated pockets of humanity, separated by gulfs of time. The speed of light doesn't just limit how fast we can travel. It limits how connected we can be. It places fundamental constraints on the size and complexity of conscious systems. Here's a thought experiment. Could there be a galaxy-spanning consciousness? A being whose neurons are planets? Whose thoughts take millions of years? The speed of light would limit how fast it could think. A single thought might take longer than human civilization has existed. Or consider the opposite. What if consciousness requires information processing at speeds faster than light? What if there's something fundamentally limiting about light speed causality that prevents certain types of complex conscious experiences? Maybe the universe we live in is just one possibility, and there are other universes with faster or no speed limits, or radically different forms of consciousness can exist. The speed of light might be why we're lonely in the universe. Not because aliens don't exist, but because they're too far away for meaningful communication. By the time we exchange messages, civilizations rise and fall. The universe is full of voices calling out to each other, but the speed of light ensures most of those voices never meet. All right, we need to talk about something that's going to sound like science fiction, but is actually a serious topic in physics and philosophy. What if the speed of light is a rendering limit? Think about video games. When you play a game, the computer doesn't simulate the entire game world at once. It only renders what you can see. It only calculates physics for objects near you. It optimizes to save processing power. And there's always a maximum speed, a speed at which the game engine can update the world. What if our universe works the same way? What if the speed of light is the maximum update speed of the simulation we're living in? This is the simulation hypothesis, and some very serious physicists and philosophers take it seriously. The argument goes like this. If it's possible to create realistic simulations of conscious beings, and if advanced civilizations would create many such simulations, then statistically, we're more likely to be living in a simulation than in base reality. And here's where the speed of light comes in. Every simulation has processing limits. It can only update so fast, calculate so many things at once, render so much information. What if the speed of light is exactly that limit? What if quantum mechanics, with its probability distributions and wave function collapse, is the simulation's way of not calculating everything until it needs to be observed? The double-slit experiment makes a lot more sense through this lens. The photon doesn't decide which path it takes until it's measured, because the simulation doesn't calculate the path until it has to. The photon exists in superposition, in a state of computational uncertainty, until an observation forces the simulation to commit to a specific outcome. The answer is yes, because c, the cosmic speed limit, is still intact. Information still can't propagate faster than c. Causality still works. What we're playing with is how light interacts with matter, not the fundamental speed limit of spacetime itself. But it raises a disturbing possibility. What if all of space isn't truly empty? What if there's some kind of quantum foam or dark energy field that space is made of, and light is constantly being absorbed and re-emitted by this field? What if the speed of light in vacuum is actually slower than the true cosmic speed limit because of these interactions? Some theories of quantum gravity suggest exactly this. They propose that at the Planck scale, the smallest possible scale, about 10 to 35 meters, spacetime itself becomes grainy, quantized. Light traveling through this grainy spacetime might experience tiny delays, similar to light traveling through glass. The speed of light we measure might be an effective speed, not the true fundamental limit. If this is true, extremely high energy photons, gamma rays from distant cosmic explosions, should arrive at Earth slightly later than lower energy photons from the same event, because they interact more strongly with the quantum structure of spacetime. Some scientists are looking for this effect. So far, they haven't found it. But if they do, it would revolutionize physics. We need to talk about something deeply disturbing: the connection between the speed of light and the direction of time. You experience time flowing forward, past to future, cause to effect. Eggs break, they don't unbreak. People age, they don't get younger. Entropy increases, never decreases. This is called the arrow of time, and it's one of the deepest mysteries in physics. Because here's the thing, most of the fundamental laws of physics are time symmetric. They work equally well forwards or backwards. If you filmed a planet orbiting a star and played it backwards, it would still obey Newton's laws. If you filmed particles colliding and played it backwards, they'd still obey the laws of quantum mechanics. But there's one law that's explicitly not time symmetric, the second law of thermodynamics, which says entropy always increases, disorder always grows. Time has a direction. But where does this arrow come from? Why does time flow forward and not backward? And here's where it connects to the speed of light. The speed of light defines the boundary between past and future. In relativity, we talk about something called the light cone. Imagine you're at a point in spacetime. Events that you could possibly influence, events in your future, are limited by how fast light can travel from you. If you send a light beam in all directions, it expands as a sphere, and nothing you do can affect anything outside that expanding sphere until the light reaches it. Similarly, events that could have influenced you, events in your past, are limited by light that could have reached you from those events. Your past is everything within the backward-pointing light cone from your present location. The surface of the light cone, the boundary expanding at the speed of light, is the division between past and future, between what could have affected you and what couldn't, between what you can influence and what you can't. So in a very real sense, the speed of light doesn't just limit how fast you can travel. It defines what past and future even mean. Without a finite light speed, there would be no clear distinction between past and future. Causality would break down. The arrow of time might not exist. But here's where it gets really disturbing. Some physicists think the arrow of time is an illusion. The fundamental laws of physics don't distinguish between past and future. The universe as a whole, the entire space-time block, containing all of past, present, and future, just exists, unchanging and eternal. What we perceive as the flow of time is just our consciousness moving along a path through this eternal space-time structure. We remember the past because our memories are physical structures that correlate with earlier states of the universe. We don't remember the future because there are no physical structures in our brain that correlate with later states. The speed of light, in this view, isn't creating the flow of time. It's defining the structure of space-time itself. What parts can be causally connected, what parts can be in each other's past or future light cones. And here's something that will keep you up at night. If the future already exists in the space-time block, then everything you will ever do is already determined. Not because of fate or destiny, but because the future is just as real as the past. You're not moving forward through time creating the future. You're following a path that already exists in the eternal structure of space-time. Unless quantum mechanics saves us. Because quantum mechanics introduces true randomness. Or does it? In the many worlds interpretation, even quantum randomness is deterministic. Every possibility happens, just in different branches of reality. In the Copenhagen interpretation, quantum measurements introduce genuine randomness, but we don't understand why. The speed of light sits at the center of this mystery. It defines the structure of space-time, which determines what causality even means, which determines whether time has a direction, which determines whether free will exists, or whether you're just following a predetermined path through an eternal, unchanging space-time block. No pressure. All right, we're going deep now. We're going to connect the speed of light to the biggest unsolved problem in all of physics. Why does the universe exist? In 1998, astronomers discovered something shocking. The expansion of the universe is accelerating. Not slowing down as they expected, but speeding up. Something is pushing the universe apart, and we have no idea what it is. We call it dark energy, but that's just a name for our ignorance. The simplest explanation for dark energy is something called the cosmological constant, a constant energy density that exists everywhere in space. Einstein originally introduced this constant to make his equations compatible with a static universe, then called it his biggest blunder when Edwin Hubble discovered the universe was expanding. But it turns out Einstein might have been right for the wrong reasons. Here's where the speed of light comes in. Quantum field theory predicts that empty space isn't really empty. It's seething with virtual particles popping in and out of existence, borrowing energy from the vacuum for brief moments. This is called vacuum energy or zero-point energy, and it should act like a cosmological constant. So scientists calculated how much vacuum energy there should be. And here's where things go spectacularly wrong. The calculated value is 10,120 times larger than what we observe. That's not a typo. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. If the vacuum energy were as large as quantum field theory predicts, the universe would have torn itself apart a fraction of a second after the Big Bang. Atoms couldn't form. Stars couldn't form. You couldn't exist. And yet, here we are. This is called the cosmological constant problem, and nobody knows how to solve it. Somehow, almost all of the vacuum energy that should exist doesn't, or it's canceled out by something we don't understand. And here's where the speed of light enters the picture. The cosmological constant has units of inverse length squared, or equivalently, inverse time squared. It's intimately connected to the geometry of spacetime. And the speed of light is the conversion factor between space and time. Some physicists think the solution has to do with how we measure the speed of light. Remember how I said we defined the meter based on light speed? Well, what if that definition is hiding something? What if the vacuum energy is causing tiny fluctuations in the effective speed of light that average out to what we measure, but have profound effects on cosmic scales? Other physicists think the cosmological constant problem is telling us that our understanding of quantum field theory breaks down at certain scales. The speed of light might not be truly constant when you account for quantum gravity effects. Maybe at the Planck scale, distances of about 10 to 35 meters, the speed of light fluctuates wildly, and what we measure is just an average. Or maybe, and this is the really disturbing possibility, the cosmological constant is exactly what it needs to be for intelligent life to exist. If it were any larger, the universe would have torn apart before galaxies formed. If it were any smaller, well, we're not sure what would happen, but probably nothing good. This is called the anthropic principle. We observe the cosmological constant to be small, because if it weren't small, we wouldn't be here to observe it. Which sounds like circular reasoning, but might actually be the answer if we live in a multiverse where different regions have different values of fundamental constants. The speed of light, the cosmological constant, the structure of space-time, the existence of the universe itself, they're all connected in ways we don't fully understand. And measuring the speed of light was the first step in unraveling this cosmic mystery that we still haven't solved. So here we are. After nearly 4 hours, we've journeyed from spinning wheels on French hillsides to the quantum structure of reality itself. We've discovered that measuring the speed of light wasn't just about timing photons. It was about revealing the deepest truths about existence. Let me bring this home to you personally. Right now, as you watch this video, photons from your screen are traveling to your eyes at 299,792,458 meters per second. But by the time your brain processes those photons, interprets the image, generates the conscious experience of watching, you're experiencing something that happened in the past? Every moment of your life is like this. You're constantly chasing the present, never quite catching it, always experiencing the past. And the speed of light is why. It's the ultimate speed limit that ensures you're forever separated from now, forever experiencing a reconstruction of what was. But here's the beautiful part. So is everyone else. When you look into someone's eyes, you're both seeing each other's past selves. You're both slightly out of sync with each other, both living in your own personal time frame. And yet you connect. You communicate. You love. The speed of light separates us from each other and from the present moment, but it also connects us to the cosmos. Every photon that hits your eye has a story. Some bounced off objects nearby. Others traveled for seconds from the sun. Still others journeyed for millions or billions of years from distant galaxies, carrying information about the early universe. You are a collector of light, a receiver of ancient messages, a consciousness emerging from the quantum fields that make up reality. And the speed at which those fields propagate information, the speed of light, is part of what makes you possible. If light speed were different, atoms would be different. Chemistry would be different. Biology would be different. You would be different. The speed of light isn't just a number. It's one of the fundamental parameters that determines what kinds of structures can exist in the universe. And you're one of those structures.